2022 Unit 5 Chemistry for Pearson Edexcel. So we're continuing with Section B. We already did a Section A in a previous video, so I'll begin with the first question. This question is about silver and its compounds. Glass decorations are made reflective by coating their inner surface with silver. This is achieved by using the reaction between silver nitrate solution, ammonia glucose, under alkaline conditions. So initially the colorless complex iron, here we have diamine silver, it's given here, forms number 1. So they ask, let me use some highlighter. So explain the shape of the complex. Because we have been given the complex here, you have to see that these are two ligands. There are two ligands there, and we have one central metal. So you position the metal and the two ligands, NH2, NH3, and here NH3. And we know that each ligand is connected to the silver using additive covalent bond because it has a lone pair on each nitrogen atom. Now you put a bracket like that and put a positive charge the other side. We know that this is going to be bond angle 180. The reason as to why the bond angle is 180 and the structure is linear is because here we have two bond pairs. This is the first bond pair and that is the second bond pair. So we see, again, the question was asking us to explain the complex, the shape of the complex. To explain it means I have to be able to know that this is linear and the bond angle is 180 and give a reason why I think it should be like that. So here I said the shape is linear with the bond angle 180. Here you score 1 mark. It has two bond pairs, of course. When a complex has two bond pairs, and here we see it has two bond pairs where each nitrogen atom within the ammonia molecule attaches or donates a pair of electrons towards the silver, and the linear structure is going to be adapted in order to minimize repulsion. So that is why you get a second mark here and the third mark here. That is how you get the 4 marks basically for that question. The next part says explain why the complex is colorless. The origin of color among complexes comes in when there is splitting of the d orbitals. If the d orbitals are split, they can be split into higher and lower energy d orbitals. Now, if there is some space or there is the up higher or lower, if there is partial, they are partially filled, it means there can be transition from the lower d orbitals to higher d orbitals when light is absorbed, and that can lead to color formation. So the reason as to why this complex of silver is colorless, it's because the d orbitals are fully filled, that there is no possibility of the electrons in the lower energy level d orbitals to transition into the higher energy level d orbitals, and that means there will be no color because of course light cannot be absorbed in order for us to see any difference in color due to the transition. So I said silver has fully filled d orbitals, so electrons cannot be promoted to higher d orbitals, or you can say there are no d to d transitions. So that's how you get 4 marks for this. Part B says the diamine silver 1 complex then reacts with glucose, forming a silver and an organic compound Y. Two other products of course form. Here we can see that even if this is glucose, we know it has an aldehyde group, and you know this is like reacting with Tollens reagent. When an aldehyde group reacts with Tollens reagent, there is going to be a redox reaction taking place. The silver in here is going to be converted from silver 1 to silver solid, as you can see here, and basically the aldehyde group is going to be converted into a carboxylic group. So this should be a carboxylic group. So we know ammonia is going to be kicked out, and then we know water is going to be produced. So this part here is some equation you can know from theory. You shouldn't have known the carboxylic acid that is going to be formed or the structure of glucose, but at least you should know that when silver nitrate in presence or alkaline is reacted with something with an aldehyde group, at least we should form silver and a carboxylic acid. This is a redox reaction. So as I balanced here, you can see we have 1, 2, 3, 4, 5, 6 oxygens, but here we have 7 oxygens. If we have 7 oxygens, it means 1 oxygen is going to come from here to make up the 7. However, water has to be formed, so this has to be 2 because we need 1 oxygen here and 1 oxygen here to balance the oxygen. So when this is 2, it means we can also balance the silver here, as we can see Here we have the hydrogens are full. Actually, if you balance the rest, this is balanced with that and that are balanced, that and that are balanced. What we need to work on is these two here. So if the other is 2, and again, this is a redox reaction. So if silver, if two hydrogens are going to be balanced the other side, it means we're going to have 2 plus 1s this side because we have a minus 1 here. Of course, in a redox reaction, the charge has to be balanced as well. So to balance the charge, this is going to be a 2. And when it becomes a 2, it means silvers are going to be 2 and the ammonias are going to be twice that, which brings us to 4. The next person says, draw the structure of Y. Of course, like I said, it's only the aldehyde group that is going to be converted to a carboxylic group. So draw exactly the structure of glucose, but this part here, instead of being an aldehyde, it's going to be shown as a carboxylic acid. Part C says, the overall reaction in a silver cell used in watch batteries is as shown. So they've given us the overall reaction. Here I use green. Let me try to get another highlighter so that we can see properly. So they say the overall reaction in a silver cell used in watch batteries is shown below. So let's see. If this is the overall reaction and they say that the half equation is this, they have given us the half equation and that is the overall. Remember again, an overall equation or overall reaction is produced by at least 2 half equations. So if this is one of the half equations, it means there is some other equation involving zinc, because you see there is silver here, of an oxide of silver. There is water, but there is no zinc. It means the other half cell should have zinc as a solid on the left side, and it should have a zinc hydroxide on the right side, so forming zinc hydroxide. Right? However, there is something here that is not in the overall equation. It means it's OH minus. If OH minus is present in one of the half cell but didn't show up in the overall equation, it means they must have cancelled out with the OH from zinc. So here we can see zinc combines with zinc hydroxide, producing, of course, 2 electrons, because these 2 electrons are going to be used up here. It means the reaction involving zinc is the one producing the electrons. So this is why we have this as the final equation, or the other half equation for that reaction. This is the end of question 10. Let's go to question 11. So question 11, we have, of course, they've given us the structure here. For we have chlorophenylamine is an amine used in the treatment of hay fever. So they have said, deduce the classification of the labeled amine group. This is the nitrogen attached to 3 R groups. This is the 3rd R group. It means it's going to be a tertiary amine. That is easy. The next one says, the compound pyridine is used in the synthesis of chlorophenylamine. So they've given us the structure of pyridine here. And they say, like many amines, pyridine is immiscible in water and the solution formed is alkaline. Explain each of these properties of pyridine. So the properties we're trying to explain are miscible in water and solution formed alkaline. Being alkaline, those 2 things. And you can see pyridine has a nitrogen, and that nitrogen should have a lone pair. If you combine this with water, remember water, there is lone pairs on oxygen. There is a partial positive and partial minus due to the difference in electronegativity, and that is going to create the attraction. That is an intermolecular hydrogen bond between the pyridine and the water. So the reason as to why it's miscible, it's because so we see with water, it's because it forms intermolecular hydrogen bonds with water molecules using the lone pair on nitrogen within the pyridine. The other part is about being alkaline. Now, of course, as this interaction happens, sometimes we're gonna, of course, this is carbon. We have 5 carbons, the hydrogens are 5 and 1 nitrogen. However, this nitrogen has a lone pair. You guys know water can act as an acid and it can act as a base. In this situation, water is gonna donate an electron. So water will donate a proton, or the pyridine will accept a proton, and therefore it's gonna become like that, leaving OH minus. The OH minus left is gonna make this solution, or this the whatever resultant solution, to be slightly alkaline, and that is why we can say it forms kind of an alkaline solution. The next part says, a student suggested that the final step in the synthesis of Chlorpheniramine starts with a reaction between monodismethyl chlorophenyramine and chloromethane, assuming the reaction is similar to that between ammonia and chloromethane. This is easy, the reaction between ammonia and chloromethane. Basically, it's you see, it's like gonna be like a nucleophile substitution reaction. They say complete the mechanism for this proposed reaction. Some of the organic structures shown have been simplified. Easy, easy, easy. Let's cancel out this and do the mechanism. We begin with a lone pair. Of course, this is a secondary amine because we have an R group here, which is a CH3, and another R group here. So this lone pair, of course, we know this is going to be due to the difference in electronegativity. We will have dipose. This lone pair is going to be attracted to the partially positive carbon, and when a bond forms, this bond goes away. When it goes away, it means it has been broken, so we produce a Cl-, which is a chloride, and then we produce a structure that is going to be like that, a structure like this. However, in this structure, nitrogen has a positive charge on it. It means this is going to be kind of unstable, and to prevent that, the bond is going to break. That's why I'm returning this arrow. This bond breaks like that, returning the lone pair onto nitrogen and releasing the hydrogen. So this step here, this one here, is to release the hydrogen. So basically, the hydrogen is going to be released, and there will be chloride in solution. These two will react together to produce HCl, and then the other product is going to be that. That is the end of question 11. This question is about polymers. The diagram shows part of the structure of a polymer formed by the condensation reaction between two amino acids. Of course, you know the amino acids have an amine part and a carboxylic part. So if we kind of separate, we can see there is a carboxylic part here, and then we have a would-be amine part here. So actually, when you look at this structure, we can see that this is where the two amino acids were formed. This is amino acid 1 and that is amino acid 2. So they want us to predict the structures of the two amino acids produced. It's easy. What we have to do is cut through here. We're going to cut through at this point. Now this is going to be a CO, connect an OH here and connect another hydrogen here to produce these two structures. It's really easy. So when you connect an OH here, you can see it forms that. And to the other side, to this nitrogen, when you connect, this is the hydrogen that has been connected, and that is the OH that has been connected to the two amino acids. The key thing is remembering where the two amino acids are connected, an OH and an H were lost. The OH from the carboxylic part and the H from the NH2O amine part. So this is kind of easy. The two structures are okay. Next, we go to part B. It says, the diagram shows a repeat unit of an addition polymer used in some food wraps. It is formed from two different monomers. Okay. They said it used the structure of the two monomers that produce this polymer. This is easy. Actually, this is addition polymerization. However, we can see there are two different monomers because this one has a chlorine and the chlorine on the same way this one has only one chlorine on that carbon. So it means if you split this into half, you are going to produce alkenes. Again, this is addition polymerization. So it's going to be carbon, double bond carbon, hydrogen, hydrogen, Cl, Cl, and carbon, Cl, double bond carbon, hydrogen, hydrogen, and hydrogen. You split them in the middle and introduce double bonds between them. That is how. These are the answers we expect. The next part says a synthetic rubber polymer has the structure shown below. They say the molar mass of the synthetic rubber is approximately 300,000 grams per mole. Calculate the approximate number of repeat units in this. The key thing is for us to find out the number of carbons and hydrogen. Again, I always advise students to label. If you cannot see, if it's confusing you, label. Label them. So I position the carbon, 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 and carbon, and then fit in the required hydrogens. Remember, in a benzene ring, each is going to have one hydrogen. And then, so we can count. The carbons are 1. Of course, we have let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 carbons within the repeat unit. That's why you see the carbons are 12 times 12. And the hydrogens are going to be, of course, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, there are 14 hydrogens. We see that. And combine the two, we get 158 gram per mole. This is per repeat unit. It means to find the number of repeat units, we're going to get the total molar mass, which is 300,000 gram per mole, divided by 158. This brings us to 198.73. Of course, we cannot find half of a repeat unit, so we just round it off to the nearest whole number, which is 1899. Actually, the allow if somebody even said 1900, but I can recommend this because it's closer to the actual number. Let's go to question 13. It says, the hydride of arsenic is a toxic gas used in the production of semiconductors. Draw a dot and cross diagram for arsenic. So assign basically AsH3. Just put AS. And then remember, you look at the periodic table and find out the group of the periodic table they are in. So this is going to be group 5. We find 5 electrons in the outer shell, so position the X. Of course, this is the bonds it has formed with hydrogen. 1, 2, 3, and now we have a lone pair left here. Remember, this is a dot and cross diagram. We position the outermost electrons on AS, arsenic, or as well as the hydrogens. That's all that is needed. So this is okay. Next, they say arsine is a reducing agent. Okay, reducing agent, and reacts with cerium 5 sulfate solution, forming arsenic. The data from the experiment are shown. The volume of arsine gas is 350. Now this is volume 350 at the pressure of that, at that temperature, and they say the volume of cerium, this is going to be cerium 4 sulfate, is going to be that. So they say concentration of, again, cerium 4 sulfate solution is that. They say complete the half equation. Of course, we begin by completing the half equation. If we have AsH3 giving As the other side, and they've told us this is a half equation, it means electrons are going to be produced. One thing we know is in here we do not have hydrogens, so the hydrogens have to come out as ions. We put 3, and therefore each hydrogen is going to be, a hydrogen ion is going to be formed due to loss of 1 electron, so 3 electrons are going to be lost, so that's easy. So the next question is telling us, calculate the final oxidation state of cerium ion formed in this reaction. Now, I usually begin such questions by writing down the key information we have. They say the volume was 488 centimeters, and they gave us the concentration. So I'm going to use these two to find the number of moles. Again, to take you back, they said the concentration of cerium 4 sulfate is that, and the volume of cerium 4,5 is that. These are volume and concentration. This information here was for arsine, and this is for cerium. So I'm going to begin with cerium and work forward or work backwards. So we have the volume, we have the concentration. I'm going to find number of moles, which is concentration times volume. We have the concentration, but the volume has to be converted into decimeters cubed. So 488 divided by 1000, and we get this as the number of moles. Now, remember these two are reacting. We have two half equations that are going to be combined. Now, this is for this part here was for cerium. Now, when we come back to arsine, we have volume is 350 centimeters cubed, and remember, if you're using PV is equal to nRT. The reason for this is we want to find the number of moles of this. To find the number of moles, it's going to be PV over RT. However, we need to find the pressure. The units have to be appropriate. Pressure was given in pascals, so that's okay. Pressure is okay, it's in pascals, but the volume has to be in meters cubed, so you have to divide by 10 power 6. That is okay. Then the temperature has to be converted to Kelvin, which is 20 plus 273. We get that, that's correct. Then to find the number of moles, of course this. Usually the watermark for you making this the subject, just substitute everything and we find that as the number of moles. They're going to be those. Now we're going to find the mole ratio. Since we have the number of moles of each, we have the moles of this and we have the moles of that, just get the mole ratio. In the end, it comes out 1 to 3. So it means, of course, I needed to find the smallest whole number ratio. So if they are going to react in a ratio of 1 to 3, meaning 1 of this, 3 of that, write the two half equations, ensuring that you put the numbers as you have found them. So imagine what I did. Write the two half equations. Okay. write the two half equations, and then, okay, they're going to be like that initially. So what we have to do is, okay, so if the ratio has told us they're going to be 3 of these and 1 of these, it means we're going to know if there are 3 of these, it means there are going to be 3 electrons that are gained by each to produce the other side. We're going to see basically 3 of them as well on the other side. And then here, if it's 1, that is going to be 1 as well, and everything is going to be 1. Now, again, it means if there are 3 gaining 3 electrons, it means each of these, it's going to just go to from +4 to 3+, because there are 3 each in +4 oxidation state, each gaining 1 electron. The resulting oxidation state is going to be +3. So that's why here you see, I say the final oxidation state of that is going to be +3. Question 14, we say that describe the reactions of separate samples of aqueous cobalt to sulfate with aqueous sodium hydroxide, excess aqueous ammonia, and concentrated hydrochloric acid. So again, here we are looking at cobalt sulfate. We have to know the 3 reactions they're going to react with sodium hydroxide, with sodium hydroxide, reaction with ammonia, and the reaction with concentrated hydrochloric acid. When cobalt 2 sulfate reacts with sodium hydroxide, a pink solution is going to form. So basically, the pink solution is going to be when it's in aqueous state. However, a blue precipitate is going to form. Remember, this is a deprotonation reaction. This is deprotonation. Yeah, I wrote it here, deprotonation, or what you call acid-base reaction. So a reaction of this complex with sodium hydroxide forms a solid, which is a precipitate basically, and water is going to be produced. This here is because some of the water molecules here, I would say 2 water molecules here, each lose a hydrogen that binds onto here and forms the water. So here you had to describe the changes in color that occur and then write an equation for the reaction to get 2 marks for this. The next part says a reaction with ammonia. Of course, when it reacts with ammonia, at first it could be deprotonation, but however they've said excess. So if it's excess, then here we're going to see a ligand substitution reaction. Remember, they said excess aqueous ammonia. That is ligand substitution. So here the pink solution forms a yellow-brown solution in a ligand substitution reaction. And then the reaction is going to be 6 ammonia ligands. So water is going to be kicked out as a ligand, and ammonia comes in to produce this. And the last reaction is about a reaction with concentrated hydrochloric acid. When it reacts with hydrochloric acid, again, this is going to be a ligand substitution reaction. But however, remember, chloride ligands are going to be bigger in size, so you cannot fit 6 around the central cobalt ion or cobalt plus ion. So what we have to do is we only use 4 ligands. So it's going to be 4 ligands, substituting the 6 ligands because you cannot fit 6 chlorides around the cobalt. So in this case, the product is going to be COCl4 power minus 2, and then we have the water ligand, water kicked out basically. So this is again a ligand substitution reaction. So this is, we were looking at question 14. Let's go to question 15. Question 15 says, a compound Q contains the elements carbon, hydrogen, and oxygen only. This is very important. So they say combustion analysis of 4.91 grams of Q produces 14.6 grams of carbon dioxide. This is good. Mass of carbon dioxide. We have it here. Okay, so they say, and 3.58 grams of water. Those two are very important. So they say, show that the molecular formula of Q is this. We are going to use this information. Now, to find the mass of carbon in carbon dioxide, remember carbon dioxide is COO. There is 12 carbons and 2 oxygens. So 2 oxygens give you 32, 1 carbon gives you 12. Total mass is going to be 44. So within this 44, 12 over 44 is going to be carbon. So we want to find the mass of carbon. It's going to be 12 over 44 times the mass of carbon dioxide produced. So carbon is that mass. Do not round off too much to smaller significant figures. Leave it unrounded off as much as possible in order to minimize the error carried forward. Now in water, because water is hydrogen, oxygen, hydrogen, and each hydrogen is 1, so it's going to be 2 out of 18. So 2 over 18 times the mass of water gives us the mass of hydrogen. Now, since we have the mass of Q. This total mass of Q should be the hydrogen, the oxygen, as well as the carbon. So if we want to find the mass of oxygen, we will get the total mass of the Q, or the compound, the organic compound, and subtract the mass of carbon and oxygen. So we get this as carbon and hydrogen. So we get this as the mass of oxygen. Now we will go to empirical formula calculation. Carbon, hydrogen, and oxygen. We put the masses of each, the atomic masses of each, and then we find the number of moles, which is basically mass over, in this case, atomic mass. We get that, and that, and then the next part is for us to find the smallest whole number ratio, or divide by number of moles. We divide by the smallest number of moles in order to find the ratio. So here I got 10.009 at 12 and a 1. This is easily rounded off to 10, that is 12, and that is 1. So it comes out to carbon 10, hydrogen 12, oxygen. This is what they wanted us to prove, so you have got it right. So here we say the empirical formula is that, and since the empirical formula is equal to the molecular formula, it means that is going to be exactly the same. Remember, they told us the molar mass of Q is 148. Another confirmation you would do, add up this. If it gives you 148, like I've done here, it means the empirical formula is equal to the molecular formula. Next part, they say the high resolution proton NMR spectrum of Q is shown below. Here it's shown here, and then they say deduce the structure of Q. They want us to find the structure of Q. Justify your answer by considering the relative peak area. So this is very important. We're going to consider the relative peak area. Remember, we have already established that Q is carbon 10, hydrogen 12, oxygen. So we're going to establish the relative peak area and everything. The key thing to understanding that this should have maybe a ring, a benzene ring in it, is look at the carbon to hydrogen ratio. The carbon to hydrogen ratio tells us that there should be a benzene ring. There is no way that is possible if something does not have a benzene ring. So if it has a benzene ring, it means we could be looking at maybe any compound, basically, provided we know these are 6 carbons and then position the other carbons. But how can we tell the rest? We're going to look at the information shown. So they say deduce the structure of Q, justify your answer by considering the relative peak area, the chemical shifts, and the splitting patterns. You will find it helpful to refer to page 8 of your data booklet. So they say the peak at 3.6 ppm is due to the proton environment of a carbon bonded to benzene ring. They gave you more information here. And then the peak is not where it might be expected from the general values in the data booklet. So they've given us this, and then they wanted us to deduce the structure of, deduce basically the structure of Q. Now, I came to this answer after what I'm going to show you on the next page. So let's just go to the next page. The next page says, remember, when we look at this environment, we can see the area ratio tells you there is a 5, there is a 2, a 2, and a 3. It means we have some, we have, like we saw, there is a ring. It means there are going to be 5 environments that are identical. Those environments are that. So let's see. There are 5 environments that are going to be identical. In this case, actually, I would say, let me just take it like this. If we draw the structure, there is one environment that is going to have 5 protons. Here we're going to have 2 protons. Here 2 protons, and this is 3 protons. So let's see, again, we're going to see different environments having different number of protons. So let's see. If you drew, if we begin from the chemical shifts, we'll look at 4 environments and 4 peaks. So because we saw 4 environment 1, environment 2, environment 3, environment 4, those are going to be 4 peaks. So we assume there are 4 different environments. And now we can see the splitting patterns. Here we have 3 splits. Here we have, 4 splits. Here we have 3 splits. And here we have no split. So this is going to be, this is basically singlet. This is also singlet, no split. This is going to be, here is a quartet. So it means in this environment, this one here has 3 proton neighbors. 3 proton neighbors. And this one here has 2 neighboring protons, okay? So again, let's go back there. So let's see. The environments are A, B, C, D. This is the structure we saw if you look at the benzene ring. And we know it's carbon 10, hydrogen I think was 12, and oxygen. So these are already just 6 carbons. So, and each has maybe, sorry, 1 hydrogen, like that. So positioning this and filling out the other carbons. Remember, they are 6, 7, 8, 9, 10. And the hydrogens are going to be 12. If you have 1, 2, 3, 4, 5, let's say 6, 7, let's say 8, 9, 10, 11, 12. Oh, this makes it. If it's going to be kind of saturated. Because if I do it some other way, you can try to do it like that as well. If you're trying to work it out. 1, 2, 3, 4, 5. Then put the carbons. Then you can say 1, 2, 3, 4, 5, 6. So that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You put a 12 here. And then you could put that. So there are many possibility or many possible structures you could make. However, you have to look at the data provided and know that this may not be right, and that is going to be the right one by looking at the different environments we have. If we had used this one here, we will have more different environments with this. It will be one environment of a proton, the second environment, the third environment, the fourth environment. There will be so many environments than required. However, so this one basically you eliminate it out immediately. And that leaves us with a structure like this. It has environments, as you can see, I labeled environment A. We have environment B, environment C, environment D. Those are the 4 different environments. When we look at the chemical shifts, environment A is about 7.4. From here, you can see about 7 point something. That environment is showing us that this is a singlet. Like we said already, this one here is a singlet, and it has 5 protons in that environment. So that is basically the ring itself, the protons within the ring. Yes. Okay. Then environment B is at 3.6. You can see about there. It has 2 protons in it. So, of course, this tells us it has 2 protons in it. And as we can see, environment C is about 2.3. It has the HCCO, of course, that. This one here, you could say it has the HCCO, but as well, the other side is attached to the ring. So, yeah, it's going to be within that range. And environment D, you can see this is purely alkyl, or it's going to be HCC, of course, alkyl, but it's far away from the ring, but it's the only one that has 3 protons. D, as you can see, it's going to be at 1.0. This is the one that has 2 neighboring protons, but it has 3 protons. Basically, it's split into a triplet. It's split into a triplet, and so basically, that is how it is. Again, this is about 1 point something. This one here is going to have the neighboring atoms are going to have those specific protons around them. So let's see, like we say, this is a singlet, this is singlet, quartet, and triplet. Using the n+1 rule, you can see it has 2 neighboring protons, which are those. That is why it's a triplet, okay? It has 3 protons in it, area ratio. However, again, to go back here, area ratio, you can see 3 protons in that environment. So we have 3 protons in here. Based on the area ratio, those are the 3 protons. However, it has basically the neighbor, or using the splitting pattern, is a triplet because the neighbor has 2 protons in it. Area under the curve, of course, this is easy. 5 protons, so represent 5, 2, 2, and 2. Was it 5, 2, 2, 2? Yeah, 5, 2, 2, 2, 3. 5, 2, 2. This is going to be 3. Area under the curve for environment D is going to be 3. This should be 3. Area of 3 for that 3. This is 3 protons in this environment. This is going to be 3 in that specific environment because, of course, the neighbor had 2, so it was a triplet. But the environment within it had 3 protons, so that's going to be 3. So this brings us to the end of question 15, and the end of benzoic acid is a white crystalline solid with a structure as shown below. It is found in many plants as it's an important building block for the biosynthesis of a variety of compounds such as plant hormones and attractants for pollinators. The role of benzoic acid in the chemical industry is also widespread, and approximately 500,000 tons are produced annually. It is used in the synthesis of many compounds, including medicine, dyes, and insect repellents. Such synthetic dyes are often classified as aryl azodyes. These dyes have a range of vivid colors and a wide range of uses in many industries, including food and textile. Their synthesis involves the formation of a diazonium ion. This ion then reacts with a phenol in a coupling reaction to form a dye. Of course, you guys remember some of these coupling reactions. The relative simplicity of the reactions involved and ready availability of starting materials make azodyes cheap to produce. Salts of benzoic acid such as calcium benzoate, sodium benzoate are used in the food industry as preservatives. So here we're seeing the introduction basically to the questions we're going to be looking at. They say devise a reaction scheme to produce benzoic acid from benzene. Now this is very important. They say benzoic acid from benzene via benzene and via bromobenzene and a Grignard's reagent. So it means we will begin with our benzene. Let me make it neat. We'll begin with our benzene. Of course, in using Grignard's reagent, there should be basically a halogenoalkane. Now, this halogenoalkane they've told us is a bromobenzene. Usually, it's going to be a bromo compound. So it means to produce a bromobenzene. You guys know we can use bromine in the presence of a halogen carrier. Let me use this as FeBr3 as a halogen carrier. After producing this, I need to make Grignard's reagent. To make Grignard's reagent, I need to use magnesium in dry ether. This combination is helping me to make Grignard's reagent, which is going to be that with Mg first and Br next. Now, since we are looking at making benzoic acid, I need to use carbon dioxide. The next step is to use carbon dioxide, and I will produce something like that. CO, Mg, Br, and finally, I can use acid conditions. Of course, this has to be aqueous, or you can say acid and water, or aqueous acid basically, to produce the final product, which is that. That is benzoic acid passing through, using Grignard's reagent through bromobenzene to produce benzoic acid. It's kind of easy, but actually some students find it hard to memorize some of the things. So if you want to be good at this, you need to practice a lot. Practice a lot with many past papers as well as some questions given to you by your teacher. Part B says benzoic acid can be used in the synthesis of azodyes. In step 1, benzoic acid reacts with concentrated nitric acid to form 3-nitrobenzoic acid. Easy. This is going to be nitration. Concentrated nitric acid using sulfuric acid as a catalyst. This is nitration. And then forming the product, which is that. So the question is like, draw the mechanism for the reaction using appropriate curly arrows, include equations showing the role of the catalyst and how this is regenerated. Easy. We need to do the formation of the electrophile. So sulfuric acid, of course, is concentrated plus concentrated nitric acid, produce NO2 plus. This one here is the electrophile that is going to attack the benzene ring. So here, plus HSO4 minus this is going to be used to regenerate the catalyst in the end, plus water. So this is the equation for generation of the electrophile. And then in the next step, the electrophile is going to attack the benzene ring, of course. So let's see, electrophile plus. Remember, this is it's the ring that donates a lone pair. Now, you have to look carefully at how this structure was done. It's here, so the arrow has to leave around this side. That is why you see I'm passing it around here, because the NO2 is going to attach onto this carbon or that carbon. So here we will produce that with a carbon OH, and then this is going to be NO2 actually. So we can do that, a positive, and the hydrogen is going to be linked out. That is the product you form, as you can see here. And then in the next step, we're going to see how the hydrogen breaks. This hydrogen breaks, returning the lone pair into the ring, basically returning the electrons in the bond into the ring, and the ring is going to close back again like that, the ring inside, and then the hydrogen that is broken away is going to be released. Finally, this hydrogen is going to connect or combine with the HSO4, which we produced already, to produce the catalyst one more time. So this is how you earn 5 marks on this kind of mechanism that is required. The next part says step 2, then 3-nitrobenzoic acid reacts to form 3-aminobenzoic acid. Easy. if this is to be converted to that, we need to use, here we're going to use tin in concentrated HCl, because this is reduction, conversion of a nitro into amino. It's going to be a reduction. This is a reduction reaction, introducing hydrogen or reducing the NO2 into NH2. Easy. In step 3, the 3-aminobenzoic acid reacts with sodium nitrite and dilute hydrochloric acid, forming diazonium salt. Now, the reason as to why they're combining sodium nitrite and dilute nitric acid is basically to produce the nitrous acid, which is basically the reagent in this step. So this is made in situ because you cannot make nitrous acid and then use it later, since it breaks down immediately. So it's good to use sodium nitrite with hydrochloric acid, but this is not concentrated, it's dilute. So they say, state the temperature at which this reaction should be take place, giving one reason for your answer. This reaction should take place between 0 to 5 degrees. The reason for this is, usually they ask, actually sometimes you should know 2 reasons. Number 1 is to prevent formation of phenol, basically. And number 2, let me just write phenol formation. And then number 2, the temperature cannot be below 0. It should be high enough to allow the reaction to continue, basically to have enough activation energy for the reaction to occur. So although sometimes people say the reaction should be below less than 5 degrees, it should never be below 0 degrees, because then the reaction will not be able to occur, because there will be not enough kinetic energy. To allow for enough kinetic energy for successful collisions, basically. Okay, so let's go to the next part. The structure of the azodie formed when the diazonium ion reacts with phenol. This is easy. Phenol is going to be, okay, but this is the diazonium ion. I'm just trying to draw it the way it was. And I'll say N2, and here we have the CO and OH. So the phenol is going to be like that. These two are going to interact. On this one here, there is usually a nitrogen, and the nitrogen, this is going to be positively charged. The mechanism of reaction leading to the formation of this is not actually required by you, but just know that something changes, and then the positive will be here, and the positive is going to be, basically the lone pair is going to be donated to that, in the end, leading to the formation of that. This is kind of like an electrophilic substitution reaction, whereby one hydrogen is going to be substituted, and we get a product. But the key thing is for you to understand that an azodie is going to be produced in that way. So this is the last page of this. Hydrated calcium benzoate is used as a preservative in soft drinks. It has the formula. This is the formula of the hydrated salt we're looking at. 2.6 grams of the hydrated calcium benzoate was dissolved in deionized water. So excess lead to nitrate solution was added, forming a precipitate of lead 2 benzoate. This precipitate was removed and dried, and the mass of the dry solid was this. So, okay. So they say calculate the molar mass of the hydrated calcium benzoate and hence deduce the value of X. I usually begin by writing equations. So if you had calcium, then carbon 6, hydrogen 5, COO, 2 of these, XH2O. And then you react them with, I think it was lead nitrate, lead to nitrate. It means actually when this is dissolved, this is dissolved in water, this part here, it's gonna dissolve in this way. This was well put. It's gonna dissolve, producing. Of course, the water is gonna be dissipated away, and now the real reaction is gonna be between that and that, because the water is not basically participating in the reaction. So it's gonna be between the calcium salt as well as the excess lead nitrate. Now, because they use excess lead nitrate, it means all the calcium salt is going to be completely used up, and therefore this is going to be completed. So, okay, so they gave us the molar mass of the salt, of PB, the product. They gave us the molar mass of the product, which is Let me see, 449. You can calculate this actually. The molar mass of the product, I think I calculated this one here by using your periodic table. The carbons are 6, the hydrogens are 5, then there is another carbon, 2 oxygens. Multiply the sum of that by 2 and then add to what you have for lead. You get this as a molar mass. The reason as to why I'm doing this is they gave us the mass of the product here, and I need to find the number of moles. Number of moles will be the mass given divided by the molar mass. This gives us that. So these are the moles of the product. So again, remember this is the reaction. This is the product, which is a solid. You found the number of moles, and the question told you to calculate the value of X. So I need to work backwards. If this is the number of moles, mole ratio is 1 to 1. It means they're going to be the same moles of this, which is the salt. So, because that is the moles of the salt, it means the previous calcium was also those same moles. So it's going to be the same thing, as you can see here, because 1 mole of the salt contained, if you can see here, 1 mole of the whole salt contained 1 mole of the whole, basically salt contained 1 mole of the calcium benzoate. So that is easy to tell that they will have the same number of moles using the mole ratio. And finally, we want to find the molar mass of the whole thing. Since we know the number of moles and we know the mass actually, they gave us this. That is the mass. So to find the molar mass, I will say molar mass is mass divided by number of moles. We have the mass given and the number of moles given, or we have calculated them. We divide and find this to be the molar mass. Now remember, this is molar mass of the whole thing. Since we know the molar mass of the whole thing, we can calculate, or we can get the molar mass of these, just subtract it. So 300.24 minus the whole molar mass of that, which is the calcium benzoate, we remain with 18.14. Now you guys know the value of X can never be, the value of X cannot be a fraction or a decimal. It should be a whole number. So if X is equal to, in this case we have water, X water is equal to 18.14. It means X is going to be equal, because this is 18X is equal to 18.14. This is going to be X is equal to 1 point something, but it's going to be a very, very tiny decimal, or very small decimal point. So we just leave it to be X is equal to 1. The whole number that is going to be the nearest whole number, basically. You cannot use decimals for the value of X. This brings us to January 2022, Unit 5, Chemistry by Pearson Edexcel. Thank you so much for being with us, and hope to see you in our next paper.